All right, let's talk about doing F-tests in R. So I'm going to use that hitters data that you used for the lab. And I want to predict salary from at bat and hits. And so this is the same question that you were trying to answer in lab 2. And my question is this model better than an intercept-only model? So is it better to use at bat and hits, or at least one of these variables, than it is to just take the average salary and guess that every single player basically has the average salary? So the hypothesis test that I'm doing here is the null hypothesis is that beta 1 equals beta 2 equals 0. And so my null hypothesis is that the at bat and the hits beta coefficients are both equal to 0. And so as a reminder, the way that I can answer this question is with an F-test. And this is the formula for an F-test, where I take the residual sum of squares for the smaller model minus the residual sum of squares for the larger model, divided by the degrees of freedom for the small model minus the degrees of freedom for the larger model. That's the numerator, and the denominator is the residual sum of squares for the larger model divided by the degrees of freedom for the larger model. And we would expect this thing to be distributed as an F distribution with two parameters, the first being the numerator degrees of freedom and the second being the denominator degrees of freedom. And so in this particular case, because we're just comparing it to the intercept-only model, this is a special case where our small model is, this residual sum of squares for the small model is equivalent to the total sum of squares. All right, so let's see how we can actually do that in R. So first I'm going to create my small model, and so this is going to be that intercept-only model. And so I do that by fitting and using the LM function, and I'm going to salary is my outcome, and I'm just going to, in my model, I'm just going to have the number 1 here because I don't actually have any predictors in this model. And then my larger model, my full model, is the one that has both at-bats and hits in it. So these are my two models. I could get equivalently the values that I would like from these models by doing what you've been doing so far, where you could do it by hand by taking the design matrix and multiplying it by, I could take the x transpose x inverse x transpose y to estimate my beta coefficients and figure out my predicted values that way. But it's a little bit faster to just do this using the LM function. If we did do it by hand, what do you think the design matrix would be for this small model? So the design matrix for the small model would just be a column of 1s. So you would just have the column for your beta naught or your beta 0, your intercept, and you wouldn't have any other predictor columns. And for the second one, it would look like the design matrix that you created for the lab, where you have a column of 1s and then a column that corresponds to at-bat and one that corresponds to hits. Okay, so how do we get the residual sum of squares from this model? Well, you did this in the lab, so you should be familiar with how to do it, but there are a couple different ways to pull out the pieces that you need to calculate the residual sum of squares. One way to do this would be to pull out sigma squared. And so if you recall that sigma value, you could calculate it by hand using y and y hat and the x matrices if you created those, the design matrices. Or you can take a summary of the model and pull out the sigma of that summary and then square it. So this will get us our sigma squared. And we know that the residual sum of squares is equal to sigma squared times n minus p plus 1. And so in this case, we have this is our sigma squared. And n is going to be the number of rows in our data set, so I can use the n row function to get to that. In the first model, p is equal to 0, and so we're going to do n minus 0 plus 1, which is just 1, so n minus 1. So the residual sum of squares for the small model is going to be the sigma squared times n minus 1. And I can also calculate this for the larger model, and so in the same way, I'm going to take the summary of the larger model, and I'm going to pull out the sigma from that summary. I'm going to square it, and then I'm going to multiply that by n, And then I'm going to subtract p plus 1, and so in this case p is 1, 2, because there are 2 variables in this model, plus 1 is 3, so I end up with n minus 3. All right, so that's how we can get the residual sum of squares. It turns out there's actually an easier way. There's a function in R called deviance, and deviance will also give you the residual sum of squares. All right, so let's remind ourselves what this equation is, and let's do it in R. So I'm going to take that residual sum of squares small that I just created, subtract it from the residual sum of squares larger, and then divide it by the degrees of freedom small minus the degrees of freedom larger. So to remind you, the degrees of freedom small is n minus 1. Degrees of freedom larger is n minus 3. And so n minus 1 minus n minus 3, which ends up becoming a plus because we've got a minus minus, this ends up being 2. So the n's cancel out, and then you have negative 1 plus 3, which is 2. So that's the numerator. And then we're going to divide that by this denominator, which is the residual sum of squares for the larger model, divided by the degrees of freedom for the larger model, which is just n minus 3. So I end up here with 33.23. So that's my f value. And now we need something to ground this in, and so we can use the f distribution to try to decide if this is a meaningful number, to decide if 33 is big or small. And so what we can do is we can look at the probability of seeing a statistic as extreme or more extreme given the null hypothesis is true. And so if we assumed that null hypothesis is true, that beta 1 equals beta 2 equals 0, we can see kind of what we would expect if what the probability would be of seeing a 33.23 or more extreme value than that, given that null. And so to do that, I'm going to use an F distribution. And so what this is doing is I'm taking 1 minus this PF is a way to calculate the probability under the F distribution. You can look into this if you do question mark PF in R. And I'm going to plug in F, which is my statistic here. So this is how I'm able to determine if there is something as extreme, or the probability of seeing something as extreme or more extreme. So I plug in that value. So I'm going to plug in F. You could type in by hand the 33.23299, and you should get the same answer. And then I plug in the degrees of freedom. So the degrees of freedom of the numerator here, because I need the F degrees of freedom the numerator and the F degrees of freedom in the denominator. So my numerator degrees of freedom is 2. My denominator degrees of freedom is n rho minus 3, or n minus 3. So that's what this is. And so there you have it. So my p-value here is 1.4 times 10 to the negative 13. So what that means is it's very, very small, essentially very close to 0. I have a very, very small probability of seeing a statistic like this as extreme or more extreme, given the null hypothesis is true. And so by that, I can reject my null hypothesis that beta 1 and beta 2 are both equal to 0. All right, so it turns out that there is an easier way to do this as well. And so, this is my model here that I fit when I did it by hand. I calculated my F statistic as 33.23. I calculated my p-value as this very, very small number. There's a function in R called Anova, and that's going to let you do this even quicker. And so here, the two arguments in my Anova function are my small model and my larger model. And so these are the outputs from the LM function that I fit. And I get this nice analysis of variance table that gives me that exact same F value, 33.233, so the same as this value that I calculated by hand, as well as the exact same p-value here, this 1.405 times 10 to the negative 13. Okay, so what if we wanted to know if the hits variable is an important contribution? So I'm just interested in this one variable as opposed to knowing if either hits or at bat are better than an intercept-only model. And so now my null hypothesis is that beta 2 is equal to 0, and my alternative is that it's not equal to 0. And so I'm going to refit my small and my larger models. My larger model is actually the same here. It's just my model predicting salary from at-bat and hits. But my small model now just includes at-bat, so that I can tell if hits was a significant contribution to this model. And so if I fit both of these models and I run the Anova function, I end up getting this result. So we end up with an F value of 15.5 and a P value of 0.0001. Great, so it looks like we reject the null hypothesis that beta 2 is equal to 0. Turns out, again, there's an easier way to do this. And so if you're just testing one variable, you can actually just take a summary of the model, the larger model that includes that variable. And this t-test that's done here is going to be exactly the same as doing an f-test where you compare the full model to one that's dropped just a single variable. And so you'll notice this t-value here is 3.948, and the p-value associated with it is the same. It's 0.0001, which is the same as this p-value here. And so we actually don't have to fit. If you're just interested in knowing if the model comparing the full model to one that didn't contain a single variable, this allows you to do that. So instead of having to fit a whole bunch of models dropping one variable at a time, you can just look at the estimates from the summary of that model to be able to determine whether or not determine whether the hypothesis testing for that specific variable. Okay, so this is the application exercise. Now for this, I want you to open R, and I want you to load the hitters data from the ISLR package. And I want you to fit a different model. I'd like for you to fit a model predicting salary from the at-bat and home run variables. And I want you to perform an f-test for the null hypothesis that the coefficient associated with home run is 0. And then I want you to compare this to the t-test obtained from the summary statement.